Now I'm going to introduce three formulas that are part of this master theorem depending on the values for a and b raised to d, and then we'll do a lot of examples after that and to capture the different scenarios and use those formulas. Okay, so let me first introduce the three formulas, and then as we do the examples we'll come back and look at which formula to use. So if, as I said, f of n should be a polynomial and monotonically increasing. So we can say f of n is some theta of n raised to d, where d is greater than or equal to 0, because n raised to d is a polynomial. So given an expression like this, for example, t of n is 4t of n over 2 plus n, we can find out what are the values of a, b and d. For this case, always compare the general expression. So t of n equals a times t of n over b plus f of n. So a is the coefficient 4, b is 2, and d, this has to be written as a function of theta. So this is n is simply theta of n. So a is 4, b is 2, and d is 1, because n raised to 1 is 1. So once we know a, b, d, we can go ahead and calculate what are the values of b raised to d. So what's the value of b raised to d? So compare a with b raised to d. So b raised to d, 2 raised to 1 is 2. So we found a, which is 4, to be greater than 2 raised to 1. So since a is greater than b raised to d, we have to use this formula where you can say it is theta of n log a to the base b, n raised to log a to the base b. So in this case, theta of n raised to log b is 2, a is 4, so log a to the base b is the formula. So log of 4 to the base 2. So that's the final result. Now we can simplify this further by using the property of logarithm. So log 4 to the base 2 is written as log 2 squared to the base 2, which is log 2. So which is 2. So log 4 to the base 2 is log 2 squared to the base 2, which is 2. So that's why we have n squared. Okay, so everyone should know log 4 to the base 2 is 2. Log 2 squared to the base 2. So the 2 with the exponent comes to the, as a coefficient. So it's 2 times log 2 to the base 2, which is 1. So that's why it's 2 times 1 is 2, n squared. Okay. So if we apply this formula, if a is greater than b raised to d, if a is less than b raised to d, we apply this formula. If a is equal to b raised to d, we apply this formula. Now if you interpret this formula a little further, we can see that if a is less than b raised to d, we say t of n is simply theta of n raised to d. And where is this d coming from? D is coming from f of n. F of n may not even have a or b values, it will have only f of n raised to d values. So if a is less than b raised to d, then it is as simple as telling the combining part of the divide and conquer strategy is more dominating than the divide part. Okay, because if a is less than b raised to d, it comes really, the n raised to d really comes from f of n. So that's the time complexity to combine the solutions. So the first part of the recursion, the division and the processing time complexity, need not be as high as the combining time complexity, which is f of n. Okay. On the other hand, if a is equal to b raised to d, this is the formula for time complexity, is n raised to d log n. So we slowly increase the time complexity multiplied by log n compared to the previous one. And it is dependent on the combining time complexity as well as the values of a and b. Then the last scenario is corresponding to what we just saw, a greater than b raised to d. Okay, Now, in order to use master theorem, one important assumption is the function f of n should be polynomial monotonically increasing, and not only that, this f of function, in order to use the theta notation, should be written as the n raised theta of n raised to d. So that's when you can use the master theorem and the big O and the theta notation. Now, if f of n satisfies these two conditions, is polynomial monotonically increasing, but it cannot be written as n raised to, you see, this n raised to d should be an integer. So it should be 0, 1, 2 and so on in order to use theta notation. If d is not an integer, we cannot use the theta notation. So in that case, we have to use a big O notation. Okay. So given a polynomial like this, the first step is to find f of n and write it as some theta of n raised to d. So when we write like that, if you cannot find a d that can fit here as an integer, then instead of theta, we have to use a big O notation. That's what I mean. So for example, here, if I write this as a theta of n raised to d, I cannot write d to be 0 or 1 because theta of n raised to 0 is theta of 1, and that is not square root of n. Then if it is 1, it will be theta of n, that's not square root of n. Square root of n is different from n. So the only way we can write theta is writing there d to be half. So in that case, f of n is theta of n raised to d, or square root of n is theta of n raised to half. So once we decide d, check if it's an integer. If it's not an integer, we cannot use the theta notation. We have to proceed by using the big O notation. So in this case, square root of n can be written as big O of n. Again, when you use big O, you can use any upper bound. So we write the smallest possible integer, such as that means we are writing the closest possible upper bound for square root of n, with the exponent inside being an integer. So we can say exponent of n is big O of n. That's the smallest possible integer for which square root of n can be written as big O of n raised to d. So d is 1, a is 3, b is 3. b raised to d, 3 raised to 1 is 3 and it is equal to 3. So it is a equals b raised to d. So if a equals b raised to d, the formula is big O of n raised to d log n. So again, you're using big O notation here. So big O of, it's the same formula, just notation are different depending on the conditions. So big O of n raised to, what is d? d is 1 and log n. So it is simply n log n. That's the time complexity of this approach or this reconciliation. Okay. Any questions? So we'll do some more examples for master